Right, yeah, so this is a topology seminar, and what I'm interested in is algebraic geometry, but I'm going to talk about mostly topology. And then maybe get some application at the end here. So my setup, topological, is X is a so X is a stratified topological space. So what I mean by that is X topological space, and I is a partially ordered set, and I have a stratification of X indexed by I. So in other words, there's a map alpha to I, and SI is defined as the inverse image of this, some I. Great, so this is just as sets, not as topological spaces, of course. Right, so I'm just breaking my topological space into different subsets. And I want furthermore that this alpha is continuous in some sense. So this I is a poset, I can give it the topology where the upper closed sets are the open sets. So it's called the Alexandrov topology. And what it amounts to saying that this map is continuous is to say SI intersect SJ bar is non-zero, implies I is less than or equal to J, and the poset ordering on I is the transitive closure of the above. Meaning, if you have some sequence of hitting the boundaries, then I is less than J. Okay, and this just actually, if you give this the correct topology, this alpha is, if you like. That's a fancy way of saying this. Yeah. Okay. So that's just the setup. And given the setup, you can define direction on your paths in X, right? So definition. So this, I might have a path in X, and I have this map alpha to I, right? And now this is a poset, and this is a poset. So I want to require that this whole map is a map of posets. So gamma is called an entrance path if first gamma then to alpha is map of posets. So I'll draw a little picture. Oh, and then I want to define this thing, length of gamma is going to be equal to the cardinality of the image in here. So this is the number of strata gamma passes through. And the picture, I didn't get very creative with the picture. So this is S1, and then this is these are touching. This is S2. This is S3. And then gamma. Gamma. It's good. When it hits a boundary, it goes from closed boundary to open boundary. That kind of thing. Okay. Question? All right, so what do we do with loops? Well, we love loops and kind of a basic course in algebraic topology. What do we do with loops? Students and I'm trying to. We can track them, yeah.
What else
Yeah.
do we do?
Yeah. We can. So we can generalize the fundamental group. So a generalization. The fundamental groupoid. Group. Yeah. Is well first. So this S. So S is the stratification. So I'm going to use. So once I have a stratification S, I'm going to put C sub S. S is referring to stratification. Is going to be called the category of entrance paths. Okay. So objects are points in X, and morphisms are paths, or entrance paths. And then up to homotopy. Okay, very good. So we get this is like a directed fundamental groupoid, which is into groupoid, just a category.
For the paths, how much of the relative to the ends? Like the ends?
Yeah, just relative to the ends, right? So if they don't have the same ends, then they're not path homotopic. Yeah. Okay. So then we also get an analog of the fundamental group. So choose base points xi and si for each stratum. Yeah, and then objects base points and morphisms are the same. Lemma such that down to 0. 1. Let's choose paths from those base points. So I mean, these categories are equivalent. Then this category I'll call C base S. This is equivalent. S by the inclusion, since any path within a stratum can be has an inverse path. That's still an entrance path. So just the inclusion is essentially surjective. And example is the one. So if I is 0 as a poset consisting of 0, and S is X, then CS is the fundamental groupoid. Yeah, star is, well, it's basically the fundamental group. Thought of as a category as well. Yeah. And you also have entrance path algebra. Let AS be the A vector space. And if you like, because you like algebraic geometry or something, K can be any ring and a vector space can mean module. Or with basis. Morphisms of this base category equals the set of base entrance paths up to path number. So elements of this are formal linear sums of entrance paths over K. The algebra structure is, well, you can multiply two paths by concatenating them. If you can, and put 0. So there. 0. Right, and then extend. I told you how to multiply two paths, so extend this K linearly. Product formal sums. All right, so example. I think we like this example. I equals 0, s equals x, right? Then this AS is the group algebra on phi 1 of x. Okay. So formal sums of group elements and multiplications really by multiplication. Then I also decided to draw this example. So this is my x, the triangle, and my stratification looks something like all of these different. Well, I'm taking the CW stratification of the triangle, so these are all different strata. Yeah. And then I can these entrance paths gives me the first barycentric subdivision of this triangle. So if I draw the entrance paths, I can go from this stratum. These are exit paths, actually, the opposite. But maybe I wanted this example to work, but okay, if I take the up, well, if I just draw them the other way, correct them the other way, and their entrance paths. All right. Okay. These are going in from this, and then here, here. So these are coming in, and I'm getting a picture of the first barycentric subdivision. Question? So the algebra is formal linear combinations of these arrows, and then if you combine them, for example, if you go like this and this, these two are homotopic. So this combination is equal to this combination. This multiplication is equal to this multiplication.
So composition with arrows contribute to the basis. Composition.
The way I wrote it there, yes, compositions of arrows do, but this arrow contributes as much as this arrow.
Much
Right,
less, but
yeah.
it's not
Right, there's one arrow here.
one.
Yeah, one basis element. Thank you. Yeah. Okay, so,
The small arrows is also of the basis.
right, yeah. So you may notice that this is also the incidence algebra of this coset. Incidence algebra. Where this means that you have so this is like K I less than or equal to J. This is, yeah. This is the basis elements are the relations of the set, okay? And then you can multiply, I don't know, I less than or equal to J times J less than or equal to K. It's, and if you don't put something, you get 0, right? I less than. And it's, okay, and so more general example then, a square is let X be any regular CW complex. And X have the CW stratification, which is what I drew in this example, right? Then AX equals the incidence algebra on the cell. That's exactly what. And you'll get barocentric subdivision if you kind of draw what the paths look like. Okay. So I don't want to quite look at CW stratifications. I want to look at just coarsenings. So I'm going to define I'm going to give coarsenings of CW stratifications a name. So a block stratification that is a coarsening of a CW stratification. Okay. And such that each SI is contractible. So example is like I can coarsen this one over here to something like, and then something like this. Right. So I just I allowed myself to glue some of these cells into one cell. Okay. And then maybe not an example is something like this, which is not contractible. Okay. But then, all right, so I have a question. None of you do. Question. What is the global dimension? This is one of the many words in my title. Yeah. What is the global dimension of this algebra? That's my question to you. So what's the answer to my question? Yeah, 5.
Corresponds to a CW complex.
Hmm?
The one which corresponds to a CW complex.
Yeah. For example, yeah.
Or just for any
Well, yeah, this is a vague question, so for any, maybe. But maybe, or the one that corresponds to the CW complex.
Length, right?
Yes. So I'll do an example. I equals 0, n equals x, and x is contractible. And the global dimension, so then AS equals to K, and the global dimension is the global dimension of K, which, yeah, if your field is zero. Okay. So maybe there's some more exciting example like the CW stratification. I will see that that one is the dimension of the CW complex. You'll find it CW complex. And anything in between can happen. It could be zero. So I'll state it this way, theorem. I'll answer my question with the theorem to myself, so maybe it was kind of a leading question. And Jesse Wong. Okay, is that the nerve of this based entrance path category gives a simplicial resolution of this AS as a AS binomial. And so in particular, since this is the nerve of length equal to the maximal path length.
Sorry, was this for the cellular or was this for the block classification?
Sorry, yeah, I should have put a assumption here. This is a block stratification. Let S be any or block stratification. Yeah. For the CW cellular one, this is this length is the CW. Sorry. Okay, and then furthermore, so now this is a CW. Well, it's essentially a CW complex. It's some kind of well, it is a CW complex, but with a stratification, with a coarsening of the stratification, right? And if M is an acyclic matching, so what do I want to say about this? If M is an acyclic matching on the cells on the path closer, then there exists a sequence of simplicial collapses so this is just discrete Morse theory. This isn't my theorem, but such that the remaining cells give a resolution of AS. as the name is. So I'm just saying you can, you can refine this resolution further, using Morse theory. The resulting complex is an analog of the discrete Morse complex. Okay. So what does this tell us? I think it was said.
David, excuse me,
Yeah.
one word is missing, maybe you said it, but I didn't hear it. A sequence of simplicial what collapse?
Collapses,
Oh,
we collapse certain cells into each other. We just, they're deformation retraction, the sequence of deformation retraction. Each pairing, like a matching is pairing cells, right? Each pairing is actually collapsing two cells together. It corresponds in this resolution to pairing off two projective modules. And removing them. Okay. So corollary is that the global dimension, it's algebra. Oh, should I go for 50 minutes or 1 hour? Whether it's
usually the center is for 1 hour.
1 hour? Okay, good. Okay, so global dimension of AS is less than or equal to the Lowy length of AS minus 1. This, by this notation, I mean the maximal path length. So Lowy length is usually that plus 1, so. Okay. And then another corollary is that the global dimension of ASCW is less than or equal to the dimension of X as this dimension, meaning as a finite CW complex. So that it's X is a finite CW complex. This specific one we know. But actually, we know better. We can actually use this to get a better bound on this. Well, this may be a better bound, but if this is a better bound, we can use it too. So I'll explain that. So it's actually just an observation. Is that if I take the entrance path algebra on CS, it's actually equal to the localization of, because I defined it as a coarsening, it's the localization of this at entrance paths. So I just formally invert all entrance paths in S, and I get this entrance path algebra on my block stratification. Just because this basically just means I can go backwards on those ones that I wanted to make into one stratum, and then that formally makes it into one stratum. All right, so this in particular implies that there's an essentially surjective functor. Okay. And now I'm going to use a new description of this algebra. So I can think about it as functors from CS to K vector spaces. And if I think about this as actually AS. And then this means that functors from there essentially surject onto functors. Did I draw it in the wrong way? No. Yes, I did. I threw this all in the wrong way. Sorry, this is the localization. So the SCW essentially surjects onto its localization. Right, and this is basically If I just take one object and parentheses, or I should put star to make it more precise. This is. Okay. Modules. So if I take functors from this entrance path category into K vector spaces, that's actually modules over this. And so now I just learned that modules over this algebra essentially surject onto this algebra. And if you're careful, this takes projectives. This functor takes projectives to projectives. Okay. In fact, it takes ASCW to ASC. AS. As a pre-module. And then these algebras are non-commutative, so you can put left or right. Okay. Good. Well, what does that imply? That actually implies that the global dimension of AS is less than or equal to the global dimension of ASCW, which is less than or equal to. Very good. And so I'll state this as a theorem now. Same author. So let S be a block stratification. So I'm only going to consider those for what goes on. Then max of the homology with coefficient K, which is not zero, is less than or equal to the global dimension. Okay, so in general, we can bound the global dimension below by the homology and above by the dimension. So the proof is actually not that. Catch it really quick. So proof, upper bound already explained, and the lower bound is if F, you consider let F be specifically the functor from PS to K vector spaces, which takes xi, a base point, to the one-dimensional K vector space K, and takes gamma, a path, to the identities. And then compute, using that simplicial resolution of the diagonal I told you about, you can compute R over this path algebra from F to F. And since you had the simplicial resolution of the diagonal, you'll get exactly the homology of the classifying space of this category with coefficients in K. And then I think I forgot to mention part of the theorem. I think I didn't write it. But we also proved this is homotopy to X for block stratifications. So this means exactly that if you have a non-vanishing homology, you get a non-vanishing X from this functor to itself, this particular module. All right. Ready? So example, X compact manifold, the block stratification, then global dimension of AS, pretty much that. The upper and lower bound are same.
Sorry,
Yeah,
I guess you didn't define BC.
yeah, I just said it in words. This
Okay.
is the classifying space. And you need to use that in common topic here. Okay,
If you're going to over it, then.
okay,
Which can be. Window text system. But it works for a compact oriented. Map. No, the example works for compact oriented. Map.
yeah, okay, you're right, compact oriented. Yeah. Or I guess I could work over,
Over Zima.
over Zima. Yeah, yeah, you're right, you're right, you're right, you're right, yeah. I mean, the example I have in mind is torus, which is oriented toward. Fortunately, so that's what I'm gonna go now to is application to algebraic geometry and the examples of torus, okay? But thank you, you're absolutely right. Okay, so, a relationship to algebraic geometry, AG algebraic geometry. But actually, since we have some wonderful members of our faculty and their students here in the audience, maybe instead, not algebraic geometry, they do study algebraic geometry, but I'm gonna put a community of algebra. Even though my title said algebraic geometry, I guess I lied. So,
Can you differ algebraic subfield of algebraic geometry?
I'm not gonna get involved in that question. So, so, I'll, instead of talking about subfields, I'll talk about subgroups. Consider a subgroup M in Z to the N. Okay, so M is just a subgroup of Z to the N, and then so I'm switching to commutative algebra here all of a sudden in this talk. So then R is going to be polynomial ring and N variables, and it inherits a Zn mod M grading. Right, because of course I can this has a natural Zn grading, and then you can take any quotient grading. Okay. So what? So well, I can get a stratification of something. So this is the multi-graded polynomial ring. Right? And you can stratify, first let's stratify Rn. Rn is going to be stratified by 0, 1, by cubes. The cube stratification of Rn. Yeah? There's a box stratification. And yeah.
What does the plus A do?
Huh?
What is the plus A?
It moves the cube around, right? The cube is starting at the point 1, 2, 3 or something like that. A is like, yeah, A is an integer value point. Rn, it's the starting point of your cube.
Yeah, though the is will be just one cube.
Okay.
If you want to specify all ends.
So here A is 1, 1. Here A is 0, 0. And I want all A's so that my cubes fill up the whole blackboard. Yeah. And those are
Tessellation.
tessellation, right? Yeah. Cube tessellation. Okay. So inside Rn, I have this vector space. This is a plane. M was a subgroup here, so I get a plane in Rn, and I can take this thing and I can intersect it with this cube stratification. So this, I'll just write it this way, this inherits a stratification from the cube stratification. And I'll call this. So I just take these cubes and intersect them with this plane. Yeah. I'll call this the bundle Ruan stratification. Because it was introduced many years ago in a over Wolfbach report of bundle. Based on joint work with Ruan.
The young green one?
No. I don't know who. Not young, but. Okay. So, actually, this descends further to a stratification. I promised a torus and I stratified a plane, so I can just quotient by M to get a torus. Stratification of S1 to the rank M, which is actually MR by M. It's torus. Okay, because you know, these are basically fundamental domains. All right, so get this stratification over torus. And what's the takeaway? Well, the consequence is what I'm interested in. So consequence, and I skip a little bit of the details. Okay, is that resolutions of AS in this particular case, as a bimodule, have this, even though this is non-commutative ring and this is non-commutative resolution, have this nice interpretation. If I take this particular stratification, they correspond to virtual resolutions. It's something about that virtual resolution, virtual projective resolution, free resolutions, free graded resolutions of R as they are R. Okay. And then I can say a little more with terms. So free, I mean R twisted by D, or D. We can say more about the actual terms in this resolution. They're of the form R twisted by D, where D is in the image of mu intersect Vn mu R intersects mu.
Since you've told us what G is, because.
Yes, I haven't finished
But
here.
not what
Yeah.
R is.
Ah, yeah, sorry, R is K adjoint X1. Yeah, exactly, three resolutions of a polynomial ring. Yeah. And D, we had this map, for say mu R is the map from, because I wrote that wrong. So mu R is the map from Rn to this quotient. And mod. This quotient map. And this D is in mu R of this first cube intersect the lattice. So this is like kind of behaves like a compact set. This is a finite set. Okay. Finite set of points in this Abelian group, dynamically generated thing. Okay. And the terms look like twistings by elements in this finite. Okay. So I did not also tell you what this word was, virtual. So I should say this because this was defined by Burkesh, Ehrman, Smith. And I don't tell you exactly what it means, but roughly means cohomology lies in a fixed Correct. Thank you. That's correct.
Sure.
Sure.
I'm a little confused about the setup here, what we're solving, we'll deal with it in a minute.
Okay.
When you said graded resolutions, you can mean graded by c to the nth over n.
Yeah, thank you.
Yeah.
Grading. That's z to the n over m graded, multi-graded resolutions of the diagonal.
So we're resolving R here, or we're resolving, this is resolution of the diagonal?
You're right, this is actually. Yeah, this is actually, yeah, but this is R. This is actually R, you're right, it's the diagonal, it's R's. Thank you.
That didn't help.
No,
Are you shifting R homologically?
That means-
Or,
right now it's a sum of R, yeah, what I mean by this. It's a resolution of the diagonal. Which is, the diagonal is a sum R. Yeah, well, twisted by these, or these and. Yeah, not that. It looks complex, but it's, that's what it is.
Hang on, are they RDs? That you're resolving by modules, but you're saying that the terms are R modules?
You're basically resolving R and all of its twists. But this is bi-graded, shoot, yeah, this is bi-graded. This is,
getting closer.
yeah, this is squared, sorry, yeah. Bi-graded resolutions of this actually inherits two different gradings based on the twist and the usual R grading. That is what corresponds to the diagonal.
And then your terms now should be like,
So
Products
the
of
terms
things as
are,
well?
yeah, R types are R. Yeah, lots of mistakes. So yeah, I was gonna do, what I just wrote was gonna be what next thing, what this means in terms of modules, right? In terms of modules, it means what I just wrote. So the next line, which now I'm out of space for, is if you take any projective resolution, a resolution of M in mod AS, this corresponds to what I just wrote, actually. So this corresponds. Now we're gonna go over here. Sorry for the sloppy board work here. Over here, this corresponds to virtual resolutions of any v to the n. There's a corresponding there's something corresponding to that.
This is a co-complex or a co-resolution or a revolution?
It's a well. Let me say honestly, yeah,
You can dualize, right, in order to both ways, or something?
honestly, you can get a complex,
Mhm.
right, of line bundles that whose homology
Yeah.
is M.
Okay,
It's,
yes,
and it's not clear which one you get.
okay, so yeah.
It depends, yeah. It depends
for
on,
this, that a virtual resolution should be, it should say the homology lies in a fixed monomial ideal.
yeah.
For this, yeah, but the
It's-
it's toric in the sense that it's the locus that you remove to make the.
yeah,
when you quotient,
yeah.
to make your stack.
yeah. Fix, okay, monomial,
Yeah,
I
it's
know.
monomial, but it's read from the fan, so.
right.
Yeah.
It's the irrelevant locus.
Yeah, exactly.
All right, sorry for the confusion, okay. But the takeaway from this board of nonsense is that this implies virtual resolutions. So we learned, right, that the global dimension of this algebra was the dimension of the torus in this case. Exactly the rank M, right? So virtual resolution of any Z graded R module. Let's see. So for any Zn mod M graded R module, there exists a virtual resolution, or at least a complex, whose cohomology is this module, okay? To this monomial ideal. Of length. Right. So, maybe not exactly stated this way, but I believe this was conjectured. By Burkett. Urban. Okay, in the same paper. In 2017. And, so this is like they conjectured it as it's this, a version of the Hilbert-Syzygy theorem. Right? Multi-graded version of the Hilbert-Syzygy theorem with this virtual world thrown in.
David, forgive me my illiteracy, but let me guess, the virtual resolution is one that you can't visualize. Is this right?
It's one where the board works very sloppy. No, it just means, it just means that we allow cohomology in some.
In some middle, so it's a complex which is exact everywhere, but one term.
No, it can have cohomology everywhere. But that cohomology lies in a fixed closed set that has to do with toric geometry. So maybe I say something, I have 2 minutes left. Maybe I can either say some history of this or I can say something about toric geometry. Yeah. I'll just try to do as much as I can. Okay, I'll say something about toric geometry. So sorry to Marud, for example, who's about to be cited and now won't be. So I can just say this. So G is from this group star. So this embeds in C star to the n. And this acts on C to the n. And you get a quotient. And I'll say a choice of good quotient of C to the n by G is called a toric variety. So it's just the orbit space of this action on C to the n, but it's a good choice of that orbit space. In algebraic geometry, you have to make some choices. Okay. And then so there's several of these. And this whole virtual resolution business is really it's resolutions by line bundles on these toric varieties. Okay. So they're what's called locally free resolutions on these toric varieties.
You mean by sums of line bundles?
By sums of line bundles. So by split toric vector bundles. Completely split toric vector bundles. So I wanted to comment on how this is related to homological mirror symmetry really quickly for toric varieties. So I'm going to just draw a big diagram in 30 seconds, 15 seconds. So homological mirror symmetry for toric varieties looks like this. So there's 100 people that have contributed to this. There's the derived category of the toric variety. So Abu Zaid in his thesis showed that this embeds into the Fukaya category of what was called the Mir-Landau-Ginzburg model. So this is some category based on the symplectic geometry of this Lefschetz vibration. This is called the Mir model. And very shortly after, there was a result of Fan, Lu, Twyman, and Daslow, which said that this also embeds into the derived category of constructible sheaves on the torus I mentioned. And in fact, Nadler and Zaslow proved this was the Fukaya category of the cotangent bundle to that torus. And if I call this functor P, then this is embedding, so this is equivalent, again, by, I'm just rephrasing this to the image of P. And this image actually is contained in constructible sheaves. Theoretically, I guess, I checked this, but this is kind of well known. It's derived category of constructible sheaves on the bundle Rouen stratification. So here, I mean, any constructible sheaf, and of course, here I just mean only with respect to this stratification that I gave you, okay? So this is lying inside here, and it's not actually equal in general, but due to a theorem of myself and Wang, this is the derived category of this entrance algebra I gave you. And in some cases, these are actually equal, and this implies mirror symmetry in those cases. Okay, and then there's a result of Ganatra, Pardon, and Gilles that says this inclusion admits essentially surjective left adjoint. So we have an essentially surjective functor here. All right, so all of that is to say that this was actually my, motivation for studying this. Is that, the complexity of the derived category of toric variety is controlled by this, derived category of this algebra. Which is just, then I wanted to understand this global dimension, okay? And this actually implies that the derived category of X, sigma, is generated by dimension X sigma triangles. So this was a conjecture first by Orlov. So this solved this conjecture of Orlov for triangles.
What's a triangle?
Yeah, so derived category of X sigma is triangulated category. So how many, if I give you a generator of that category? Yeah, how many distinguished triangles do I need to build any object from a fixed generator? So if that generator is the image under this essentially surjective functor of AS, the number of distinguished triangles will be at most n. Not the same, not this number. Rank M. Yeah.
Which thing? That?
Mhm, yeah, that's it. Right.
Any questions?
Is there a relationship between the right-hand side here, the Fukai category, and these other things as well?
Yeah, I didn't mention that one, it was supposed to be in there, you're right, so, this one, this image is also this. So once you realize it this way inside here, if you take this image, inside here, we take, I don't know, image of E composed with psi, right? Then, these two things, I want to say are equal by, I'll do 300 part of this.
Oh, that makes a nice.
Actually, it is a sequence of 3 terms. So this story originated here. Buzaid and Fanlu Tremon Zaslow's work. And there's been a lot of development connecting all of these things to kind of fill out the homological symmetry picture now. This, I think, because you mentioned it at some point, this is passing through this correspondence with what's called Fukai category with stops. So you take this Fukai category of the cotangent bundle and you throw in stops, which are points where the Lagrangians can't flow past. And the stops are precisely the limit of the limiting, basically the tropical limit of this the fiber over its W. And see that's how you get it. Yeah.
So in the case, if the case is on a field, can you say anything about kind of the global dimension of these algebras, in combination of the global dimension K and the?
That's a great question. I think you can bound it by the sum. And I don't know beyond that.
Perhaps your results will tell something about the relative dimension over R.
Yeah.
Over the ground plane.
Yeah.
Over K.
Yeah. Yeah, well, you still get, certainly K, you get this simplicial resolution by the nerve can work for any ring. So you have a resolution of that length of it as R module, you know, O. So. Yeah, but then the diagonal is only going to feed in.
If you're dealing with just posets, there. And I think what you're saying is correct. Like when you take these resolutions, you see what's happening at each element of the post set, and you end up with a module which you can resolve by your ground ring. And I think ultimately the global dimension will be at most the dimension for the post set plus the dimension of the ring. I think it works.
Okay, that makes sense, yeah. I think that works, but I haven't thought about it. Also, yeah, I mean, there's results, like Peter's saying, there's results on global dimension of incidence algebra, for example. There's other stuff about this where incidence algebras on cell post sets are known to be visual and therefore have dimension. Those CW ones that I was trying, those are not.
The resolution that you were talking about close to the end of your talk, before moving to the big diagram, for example, those resolutions allow you to come up with the basis of the derived category.
Generated category, yeah, I mean, it's going through this abstractly, but in fact, so in the paper that I put out on this, which proved this conjecture, we explicitly traced what this goes to in the derived category, and it's a sum of line bundles. Or if the torque right is smooth, it's a sum of line bundles, and in general, it's a collection of sheaves. Corresponding to
Shapes in the sense of compensating shape.
no, just sheaves on the nose down. Yeah, but actually on this side at the level of constructible sheaf complexes of constructible sheaves, it corresponds to actual complexes there. Yeah, so actually in the algebraic sense, it's a nicer thing than on the.
Other questions? Okay, let's think David's an interesting talk again. Thanks. I want to advertise the department, like David Truman was an undergraduate in our department. That's T over there, this huge diagram. And Kaya, FUK, and the huge diagram, will be visiting us and giving a colloquium and maybe even more lectures next week as an Ordway visitor. Kaya will be here.
Great.
Next week.
Good. Oh, yeah.
I should stop the recording. Yeah. 6 years off the record.